Okay, so today what we're going to do is we're going to wrap up our discussion about work equals the change in the dynamical energy. And as I mentioned a few minutes ago, we were using U equals delta E. Delta E is our change in this energy, which is made up of the change in the energy of motion, the kinetic energy, plus the change in the gravitational potential, plus the change in any elastic potential that exists in the system. And after we've done a problem or two in that area, then we're going to go ahead and introduce the concept of linear impulse and momentum, which is nothing more than a variation on F equals ma. Okay. So I thought what we might do today, first of all, see if there's any recent questions on the material that you folks might have, thing you've been struggling with.
Was giving you a stroke pause. It's back in the kinematics.
I'd rather not go that far back.
Okay.
Just come see me if you can, okay, on the kinetic stuff. There is a topic back there I do want to bring up on another day, though, and I want to give you actually a handout sheet on that, but I haven't got it prepared yet. How about more recent material on work energy stuff? Anybody? Okay. So I have a problem in mind then that we can tackle using the work equals change in energy, where there's some rotation involved, which is similar to what you have assigned in a few problems. So here's a mechanism pinned at this location on a 300 millimeter arm, roughly close to 1/3 of a meter in length and a 6 kilogram mass out there. And then hinged to that is this 4 kilogram mass, which can move up and down in this frictionless slot. So what they're saying is when the angle theta between these two arms is 60 degrees, it's at rest. And then the 4 kilogram carriage will start to fall as the 6 kilogram mass rises up in its rotation. So we want to determine the velocity of the sphere, the 6 kilogram mass, when theta becomes 180 degrees. In other words, when this is perfectly vertical. The rotated mass is now up at the top. And we're going to neglect the mass of the links, which would just make the problem a little more exciting if we included that, and the inertial effects of because of their rotation as well. And so we'll just ignore those at this point. And they've given us an answer, so it looks like it's very close to 1 meter per second for the final answer. So what reason I wanted to do this is you have some assigned problems where you have arms in rotation like that. So let's go ahead and sketch it up and see where it takes us. So we have the arm pinned, extends down. Are those equal length arms of 0.3 meters? Equal length, okay. And then is the other arm, what's its length?
0.3.
All 0.3. And then directly under here is where this mass sits. I'm just going to treat it like a cylinder. And it's locked in to be able to move vertically. And this is the angle defined as theta. And then up here on the end of this 3 kilogram arm is we have this 6 kilogram mass, and I believe this one was 4 kilograms. Okay. Now what would be useful to include on this is the path followed by the rotating body, and then also include any active forces. And so we have the weight here, which is going to be 6 times 9.81. And then we have the weight of this body, which is 4 times 9.81. No friction in the system. Okay. if we're working this out using work equals change in kinetic energy plus change in gravitational potential plus change in elastic potential 0. Are there any forces doing work, active forces doing work here? There is some loading in this bar. There is some loading in this bar.
Rigid, and that they aren't going to move, and we can say they won't store any energy.
They are rigid, that's true. They are rigid.
There's a force in the direction of the bar, is what you're saying.
Okay, they're equal and opposing forces inside the bar, and there's some effect going on through the transition through the pin over here. In a static configuration, this is at 60 degrees when we let it go. In a static configuration, before we let it go, this bar is carrying what?
The weight of the ball.
Is it carrying compression or tension?
Compression.
Carrying compression. And there's some bending in there too, isn't it? Okay. There's some bending because of the lever arm here, and there's a component of this weight that actually creates a moment about this pin. Now that moment is what's actually creating the rotation. And there's some compressive loading going on in here. There's also the support forces offered by this pin support. What's this member carrying down here in the static configuration? Tension, okay. And if that's carrying tension, then that means it's pulling on this. If it's in tension, it's pulling on this pin, which is putting this into some bending, so forth. So now the question is, if this member is in tension, is it doing work as it moves through the motion, or can we neglect that?
As it expands and contracts, it will be doing a bit of work, but not very much.
Okay.
Component of that force that's parallel to the movement of the 4 kilogram weight.
Okay, there's a component of the tension here that is contrary or opposite this load, this weight. So there's a component of force here this way that's in this member. Someone was commenting about the fact that if I cut that, there, by equilibrium compatibility, there's equal and opposite forces that exist throughout that member all the way through, including the lateral forces that we're not concerned with. The lateral forces that are in there, the bending, the ones that would contribute to shear and bending. Okay. Similarly, in this member, in these members, they would be equal and opposing. So we're not going to have to worry about them, to make a long story short. So now, just using our governing equation and just using the fact that we only have the gravitational weight terms here giving rise to a change in gravitational potential, then there's no other forces doing work. So when this U is equal to 0, we call that what? When U equals 0? Conservation of dynamical energy. So we have conservation of dynamical energy going on. Our delta E is equal to 0 in this problem. So there's just, again, like a problem we did previously the other day, a balancing act, a trade-off going on between these changes in energy, the energy of the motion and the change in gravitational potential. So what we need to establish is a datum. So I think probably the pin location would be a good spot for our datum. As good as any. And let's see. Since this triangle remains isosceles, we could define distance down to this mass as some distance called, say, y. And it's related to 0.3 and angle theta here. And we'll have to do a little trig on that, a little trigonometry. And then we'll be able to work on defining the change in potential here. Okay? We've also defined y pointing downward, which means positive sense of the velocity of this mass, 4 kilogram mass, would be downward, and its acceleration would be downward. The positive sense of those. Okay. What's also missing on here is a lateral force exerted by the sidewall. Call that just a normal force. Any work done by that? No work done by that because there's no displacement in that particular direction. Okay. Okay. Now, if this is isosceles, I guess we better look at a little more geometry here. If we have an isosceles relationship here with this defined theta, and that being 0.3 and 0.3, then if we split this in half horizontally like this, then that means half of theta is the angle that this mass sits above the horizontal. So this angle is theta over 2. Why do we want that? Yeah, so we can look at the vertical distance that this body initially was at, and when this thing finally goes through some rotation, what its final elevation is relative to this angle theta.
Could we simplify things by calling the distance the sphere is above the datum just 1/2 y?
Well, we might. You see what Daniel's observation was? Could we just call the vertical position of this half of y?
It looks like it will be.
It looks like it would remain. We could do that. Right. So that would be a choice we could make. And so let me just put that here, and let's see. And this would be, if we define y this way, we got to be a little careful, don't we? Then that would be, its magnitude would be half of y, and I'm just going to put absolute bars on that. Okay. Well, and actually, I don't even think I need to do that, absolute bars. Why not?
It's going to be positive?
Yeah, because this is going to stay positive, is it not, in its defined sense here? In its defined sense here, this is going to stay positive, so those absolute bars wouldn't be necessary. Okay. So, what I'd like to do, though, is let's go ahead and write it in terms of theta. Let's write the problem in terms of theta, and then see where that takes us. So, change in kinetic energy, or the energy of its motion, is going to be the 1/2, and we have this mass, 6 kilogram mass, that's in motion, and it's got some speed. Which is what? It's got a change in speed occurring. It's going to have, I'm going to call it, let's call it V sub 6, because that's the, and that's going to be at some generalized theta. Do I want to do double subscripting? Minus the speed that 6 kilogram mass had when it started. Plus, we also have this other 4 kilogram mass that has a change in kinetic energy too. So don't forget, we're dealing with a system here. And so this is going to be the speed it happens to have at some location y minus the speed it had y at the initial location. So that's the change in the kinetic energy of the system. And we have to add to that the change in the gravitational potential reference to the datum. Reference to the datum. So we're going to add to that the weight. So we have the 6 kilogram mass times 9.81 mg times its height at some theta minus its height initially. Reference to the datum, and then we have to add to that the change in the potential, gravitational potential of the 4 kilogram mass, 4 times 9.81 times its height, and so that's going to be y at some theta off the datum minus the y, and actually I better call it h. Let's call it capital H at theta minus capital H initially. And that sum of those changes in energy must be equal to 0. So let's put in the parts. They told us at 60 degrees, theta equals 60 degrees, we're at rest. So that was our initial conditions. And so that is going to mean that this initial speed was 0 for both masses. And we can then work up the geometry here. And we're going to need this initial y position that this was at when this was 60 degrees. So what we can do is look in here and see that the y is made up of these two pieces, and each of those pieces is 0.3 times the sine of theta over 2. .3 times the sine of theta over 2, and the sum of those is equal to our y value. So continuing on, y is then equal to 2 times the 0.3 sine of theta over 2, or 0.6 times the sine of theta over 2. At 60 degrees, the y was equal to 0.6 sine of 30 degrees, which is then equal to 0.3. Which is this distance at the starting point, which, using the symbolism in here, is the 4 kilogram masses value below the datum. Now we have to be real careful there. The HI, this is equal to, so 0.3 is that H, is that capital H initial?
Yes, and define y.
But be careful. Here's the datum. It's below the datum. The Earth's gravitational attraction is down below us, so it's below the datum, so that capital HI is actually a negative value initially. So this negative here is not, so what I'm trying to get at is that capital HI has to be assigned a negative value. So this has to be, the capital HI has to be a negative 0.3 because it's below the datum. Okay. At any theta then, in general, at any theta, it's going to be still below the datum, isn't it? Still going to be below the datum, and it's going to be this value except negative, isn't it? Still below the datum. So the H sub theta in our energy equation is going to be the negative of this 0.6 sine of theta over 2. So that takes care of the 4 kilogram masses values we need in our equation.